You.
Okay, and then Arash, I need you to stop sharing your screen. Okay, I can share mine. Um, okay, and I guess you can see my slides now, right?
Yes.
Okay,
Thanks.
correct. Well, thank you very much again for the invitation. The topic I wanted to share with you today is on one of my projects focused on the resiliency of distributed energy resources and solar infrastructure to earthquakes and hurricanes. Um, and let me start by showing you this picture here. This is Puerto Rico pre and post Hurricane Maria in 2017. This picture, I like this picture because it's self-explanatory. It shows this nighttime satellite imagery and shows the extent of damage to the power grid that the hurricane caused. Millions of people lost power for several months. This is the longest and largest outage in the US modern history. And I usually use this example, but now there are more and more examples. Hurricane Zeta, that was a month, 3 weeks ago, it caused 2.6 million outages in the southern part of the US, all the way through Georgia and the Carolinas, causing massive outages. It's not only hurricanes. The 2014 Napa earthquake caused 70,000 outages in California, and that was just a medium-sized earthquake. And with the wildfires in California, also we're seeing that the power grid is truly vulnerable to disasters. So that's the motivation of this piece of work. That together with the introduction of distributed energy resources. And what happens with a traditional power system is that it's vulnerable because it has some features that make them vulnerable. The first feature is that the system is heavily centralized. That means that generation occurs far away from the cities, and it has to travel through distribution and transmission lines that many times are quite vulnerable. And you're seeing here a picture of how these lines fell from winds or just trees falling into the wires. And they have low redundancy. So small failures in some parts of the distribution grid, the transmission grid, can lead to massive outages, as we've seen in these previous disasters. However, the system is changing. It's changing a lot. People are now generating power basically on the rooftops with, for example, solar panels, and that's distributed energy resources. The system is being decentralized, and that has the benefit of reducing the dependence of the consumers on these vulnerable power grids or vulnerable distribution lines. It's growing rapidly. Here's some statistics of their growth. PVs, photovoltaics, or solar panels have been growing at the 7.5% rate, and I think now it's higher. This is, I think, a little bit of an old statistics, and expectations are high. I mean, this is quite variable, but the expectations say that global generation by 2050 is going to be 20% solar or more, right? So given this expectation, my focus is on how these distributed energy resources might change the resiliency of the power grid, of the traditional power grid. And that together also with um, microgrids. Microgrids is not a new technology. It's been on for a few decades. And what a microgrid is just a cluster of people consuming customers or loads and distributed energy resources that can share energy. And one of their key features is that they can work on island mode. That means that when the main grid is out, they can still work with their own generation. And there's some evidence that they've worked successfully after a few disasters. For example, after the Tohoku earthquake and tsunami in 2011, the Roppongi and Sendai microgrid worked really well. And just to remind you, this was a massive earthquake that led to the Fukushima meltdown and extensive power failures there. They also work after hurricanes in the HEV store. They had a microgrid, and that worked in 2017 after Hurricane Harvey, and it worked so well that emergency responders use it as a base for operations after the hurricane. And while we understand as a research community, we understand much better what's the economic and the environmental benefit of distributed energy resources, the resilience question has been avoided. Well, not avoided, but people haven't addressed that yet. And so those three components are the motivation of what I'm going to show you today. I've divided the presentation in two parts, and I'll finalize with conclusions. First, I'll focus on how these new technologies can help us be more resilient to earthquakes. Then I'll move to hurricanes. And as I said, I'll finalize with conclusions. Let me start with earthquakes then. So here we ask the question of whether a neighborhood with distributed energy resources and a microgrid can be more resilient. And for that, we develop here a model, a framework to couple earthquake analytics, as we do in risk analysis, with distributed energy resource generation. In this case, we focus on rooftop solar panels in California, as you are seeing here in the picture. And we focus on the behavior of microgrids, seeing on how these neighborhoods can share energy to have more accessibility to power, more access to power when the main grid is out. And we apply the framework to California, to San Carlos City in California. This, we work with Professor Ankirimijan and also Professor Ram Rajagopal, joining expertises, and also Dr. Sid Patel now joining expertises from the electrical engineering side and also civil engineering, and also with the PhD students, Chenin Liu and Tausan. So here is the framework. I have there are a couple of publications here that you can check for the mathematical formulation, but here I'm just gonna describe it conceptually. What we wanted to see is that if this is San Carlos and you have in gray polygons here, you have the footprint of the houses, and then you have also the solar installations in yellow dots. What we wanted to see is whether if a neighborhood that it's enclosed by this red circle, for example, adopts a microgrid, we wanted to see whether there we measure as risk as the likelihood of they not meeting their demands for power after the earthquake. So it's just the probability of demand exceeding supply here in this entire neighborhood that shares energy. Again, here we focus on rooftop solar panel, and just to remind you or give you some context, solar generation is highly seasonal. You have more generation during the summer than during the winter. Therefore, here the risk is going to be coupled with the season, which is interesting because that's not usually the case for earthquakes, as it is for other natural hazards. So here in this framework, we again extended or base our analysis on this extension of the PVE or risk analysis framework, where we first assess the hazard through the ground shaking, then we assess the vulnerability or exposure through the damage state, and then at the end we measure our decision variable was the post-earthquake power load in the microgrid, how much people consume or need, and the supply that the microgrids and solar panels were able to give. And I'll just walk you through them one by one. So first, for the ground shaking here, we assessed a repetition of the San Francisco 1906 earthquake of magnitude 8. Sorry. You can see that it's a massive rupture through the San Andreas Fault here. We use ground shaking as a ground shaking model. We use average spectral acceleration that Professor Davalos and Professor Miranda developed a few years ago with its own spatial correlation, which they show to work well for the kind of houses we see in San Carlos, wooden houses. And San Carlos City, our case study is here. The plot I was showing you before, that was the footprint of San Carlos City. So then we assess the damage states here. We assess whether houses would be red tag or not for 1-story and 2-story houses. We got the exposure data also from tax assessor data in California, which is quite a comprehensive data set that gives you data building by building. We work with the fragility functions developed by Professor Eresi and Professor Miranda, developed 1 year ago. And notice here that something interesting is happening because the solar panel is on top of the house. Now the house becomes the supporter pillar of that generation. If the house is down, likely you're not going to be able to to harvest power from the panel anymore. So as like that's a main difference from the it's kind of an intuitive difference and seems but quite relevant. Now the infrastructure, the housing infrastructure and the power system infrastructure are coupled together, which is interesting. As I said, we collected data we got data for San Carlos City, and that's close to 8,000 buildings, residential buildings. And out of our analysis for this earthquake scenario, we saw that one-story buildings have, or two-story buildings have higher probability of collapse than one-story buildings, 8% versus 1% for this scenario, as a result of the larger vulnerability that Professor Iresi and Miranda showed for two-story residential houses. So then we move to that third part of the analysis, which is subdivided into two parts: the demand and the supply. So here for the supply, for generation, how much you can generate after an earthquake. First, we measure generation or weather irradiance, and we focus on global horizontal irradiance. And we took that generation from, or those records from, the Bakersfield Weather Station. And you can see here is the dot in California on the map here. And you can see here that generation varies according to the time of the day. You have lower generation when the sun is down, but when the sun is up, you are at noon or 2 or 3 p.m., you have the highest generation. And also generation changes by month, by season also. You have higher generation during the summer and lower generation during the winter. So we incorporated that into our analysis. We did some probabilistic modeling there using a beta distribution with some previous work that Professor Roja Gopal did with Lair and also with Dr. Patel. So that's and then for generation, we also use computer vision results of where solar panels are in California. This is a work that also Professor Roja Gopal did at Stanford with satellite imagery and computer vision techniques. There's data now of where solar panels are in the entire US and how big they are. So we use that also in our analysis, and we saw that in San Carlos, only close to 8.5% of houses only had solar panel, which is still, I think, a low adoption. And then we coupled that with damage state. Basically, we said that if the house is red tag, then you're not going to be able to get power out of the house. And then that's one side. The other side is the demand. For the demand, we're very lucky because we got access to a smart meter data for a lot of houses in California, and that's just recording of our hourly consumption, power consumption for an entire year. So we had those recordings, and we could see even differences of consumption between summer and winter. So we incorporate that in our analysis. Obviously, the data is anonymized for privacy reasons, so we did some stratified sampling according to the building area to map those records to the houses in San Carlos. And then in our analysis, we considered that, or we focus on providing houses with basic consumption that supports basic needs, like refrigeration and air conditioning. So we took an assumption and reduced their consumption by 30%, to 30 or 50%, just assuming that they, in a state of emergency, they will consume less if they are able, with a goal of sharing more energy between the neighborhoods in a microgrid. So the second part of the analysis. And then the last piece is how we model microgrids. And here we model microgrids as a neighborhood that is able to share energy between each other. And we took inspiration on the concept from the Brooklyn microgrid in New York, which it's already working, but they share energy to neighbors in close proximity if they generate more than what they need in their own households. So here we didn't focus as much on the infrastructure required to build a microgrid, because that's changing a lot over the years, but just conceptually to see how sharing energy between houses that are in close proximity can help you be more resilient to earthquakes for the power grid. So we model potential microgrids as a cluster, using a k-mean algorithm with same group size here. And we tested multiple microgrid sizes here. So this is just an example of microgrids, of potential microgrids of 20 houses that can form in the next years in San Carlos City. And this is the last piece of analysis. And then we put everything together here. And this for this earthquake scenario, we assess what is the likelihood or the risk, the probability that each cluster meet or fails to meet their demands after the earthquake. And the closer you are to 1, that means that your risk is higher. That means that you haven't met your demands. And here we subdivided the analysis, or we performed the analysis for different seasons, because there's a strong seasonality in effect in the on this risk metric here. And as you can see here, each dot represents a microgrid, a particular cluster, and a lot of them are close to 1, meaning that 8.5% adoption is still very low to sustain even these basic needs after an earthquake, if the earthquake knocks down the main power grid. With that said, you can start seeing that in the summer you have a little bit of a better performance, because in summer you have higher generation here. So you can see some of the grids can start being close to 0 risk. So a few are close. But we didn't stop here. We said, okay, this is a peek to the present, but let's see what happens in the future when people start adopting more, and what implication that has for resiliency. So we assessed 2 potential adoption policies here that are based on net zero. Each house adopts as much as they need for a year on average. On one hand, we assess an overall adoption rule where adoption is based on absolute savings. And that means that an absolute savings is correlated with household electric consumption and income. And interestingly, under this adoption, what happens is that the largest houses are the ones who are going to adopt solar here under the overall rule, that it's driven only by pure economic saving. So then we tested a bit of a different adoption to make it more, to make the solars more spread over the city and not just in the rich neighborhoods. We said, okay, let's test a more even adoption rule, and in that we're going to let the adopters be the ones who save the most, but within clusters. And the clusters you saw, they are spatially distributed across the whole city. So in this second policy, you can see a more even adoption, spatial adoption here. And we tested these 2 policies and the implications for resilience and risk. So these are the same plots that I showed you before for the overall and the even adoption, and for the overall and the uneven policies and their different adoption rates. And let's focus first on the overall. Well, let's focus first on what happens at a 20% adoption rate. And you can start seeing that when you get to this adoption rate, instead of 8.5, you can see that the median cluster gets its risk decreased to close to 0.5, which is a lot from what it was before, which was like close to 1. And these results are again for an average for the entire year, considering averaging all seasons here. So that's the first thing you start seeing. With 20% adoption and upwards, you can see some benefits for resiliency, significant benefits for resiliency. The second thing you see here is the difference between the boxes under the even and overall adoption rule. And here what you can see is that under the overall rule, the boxes in the overall rule are quite wide, whereas in the even adoption rule, they are narrow. And that means that under the overall adoption rule, several clusters are going to perform really well, but the neighborhoods that don't save the most with this under this policy, save the most, get a solar panel, do really poorly. Whereas under the even adoption rule, you start fixing that. So with this kind of framework, with formulating this kind of framework, testing this kind of policies, you can start seeing not just resiliency, but equitable resiliency across the neighborhoods in San Carlos. So this was one of the main conclusions out of this analysis. And this is the analysis for the entire year, and this is the analysis for the summer. And in the summer, you can see that things are better. The risk metric decreases much more. For a 20% adoption, you have close to zero risk of the median cluster for the summer. However, the disparities that we saw under these rules, the difference that we saw under these rules still hold in terms of equality, equitable resiliency. As you can see, that there are still larger boxes for the overall rule than for the even rule. So this is what we did for the earthquake hazard. We built a framework to model risk and how these distributed energy resources and solar infrastructure can give you power accessibility after an earthquake. And we measure that through our risk metric. And we saw also what are the implications of different adoption policies for equitable resilience. So that's what I had for earthquake hazard. And now we're going to move to hurricane hazard. And here, we had a similar idea of measuring resiliency and risk under hurricane hazard than we did for hurricane hazard. But here we were going to focus more on generation. And instead of focusing on a city, we're going to see a more macro analysis. The objective here was to merge hurricane analytics with solar generation during hurricane cloud conditions. And we're going to see that these two factors are quite seasonal also. And that we're going to couple with solar panel vulnerability. And we're going to apply this model to the entire East Coast of the United States. And here we work with Professor Ling here, who leads the work on synthetic hurricanes and storm modeling, and also the PhD student that she and also it's in collaboration with some researchers in the Andlinger Center here at Princeton that focus on energy and the environment. And here I'm just showing you a picture that shows that solar panels do fail under high wind conditions. So for this analysis, and here I'm just showing you again the framework. I have a publication that I haven't put here, a preprint that kind of walks you through the math behind this. But here we're going to focus on accumulated generation during a hurricane emergency. And we're going to see that solar panel generation now is strongly coupled with hurricane conditions through the hurricane clouds, through the hurricane winds, for example. And we've decomposed this analysis into pieces as we did for the earthquake hazard. We start with the hurricane intensity here and creating synthetic storms to represent what happened in the past statistically. It's a combination of physics-based and statistical simulation of hurricanes. I gave you category, wind speeds, hurricane eye location that are key for this kind of analysis. We're going to couple that with a quite new model that we've developed that assesses how solar irradiance decays during hurricanes because of the cloud conditions. And then we're going to couple that, as I said, with solar panel functionality, vulnerability based on their structural failure driven by high wind conditions. And at the end, we're going to measure solar generation as a time series of what happens after a few days after the hurricane makes landfall. And now I'm going to walk you through each of these steps here. For the hurricane catalog here, we're working, as I said, with synthetic hurricane data based on a mix of physics-based and statistical models that are based on global circulation models and can potentially capture climate change. So this analysis was done for current climate, but we're expanding this analysis for potential variations in hurricane conditions associated to climate change. As I mentioned before, we do full tropical cyclone modeling, its genesis, its tracks, and its wind profiles. And here I'm showing you just a couple of pictures here, one with several realizations of hurricane tracks and the other one with 2 tracks, and showing you some of the radiuses. I should put labels here, but one is the radius of maximum wind, for example. The other one is the radius of winds of 34 knots, for example, which are key measures for hurricane intensity. And here we model close to 5,000 hurricanes, all the way from tropical storms to category 5 hurricanes. The second piece of analysis was based on irradiance. And this is an irradiance map. This is a global horizontal irradiance map in kilowatt per square meter of solar panel. Obviously, this has to be multiplied by some efficiency that the solar panel has. But this is what drives irradiance. And this is a picture that is showing irradiance at 3 p.m. UTC on August 29 of 2006. And you may ask, oh, why is you're being so specific with this plot in terms of date? And that's because I want you to focus also on what happened exactly 1 year before, in 2005, when Hurricane Katrina made landfall around close to Texas. And you can see here, as the plot becomes bluer in this site, that irradiance decreases during hurricanes, and this is mostly due to its cloud condition. Doesn't have to do with this part, at least doesn't have to do still or yet with solar panel failure. It's all cloud conditions. And the thing about hurricanes is they are massive, so you can have these reductions in solar generation through very extensive geographical regions here. So here we did an extensive analysis of what happens with the past hurricanes. We collected data for the last 20 years of hurricanes that were significant. Um, uh, and we define significant by being of a category 3 or more after landfall. And we couple this data set with NRL solar irradiance data. This is a data set for irradiance in the US for the last 20 years. And it's a quite large data set. We're talking about like 100 gigabytes of just data on the points of interest. And then we did a statistical analysis on how different hurricane features make irradiance decay during the hurricane. And here, what you're seeing here in these two plots are a measure of irradiance decay. It's just the logarithm of the irradiance recorded during the hurricane over its median under normal conditions. And you can see that in the plot, in the upper plot shown the upper part of the slide, you can see that the decay is more intense closer to the eye of the hurricane when D is closer to 0. And this is just the distance from a side of the recording to the eye of the hurricane. And if you move away from the eye, you recover back to normal conditions. And that means that this delta here gets close to 0. That's when the log gets to 0, and that means that the irradiance during hurricane conditions is similar to the median of irradiance during normal conditions. We also saw that category is a good predictor of irradiance decay. As you can see here, the higher the intensity of the hurricane, the more decay you have. So this is just a summary of what we saw. So we saw that we focused on these two predictors, and we created here a model based on mixed effect regression. And this is quite similar. Just let me check that. Okay, I'm okay with time, I think. And this is just quite similar to what we do in to model ground motion prediction equations. Same technique. Here we're splitting variability between spatial variability and temporal variability, measuring irradiance in different places at different time steps of the hurricane, but same technique here. And we assess multiple what we call functional forms, one that varies irradiance decay according to the category, other ones that have some correction for short distances, as we do in ground motion prediction equations, and one that's a little bit more complex. And we ran this mixed effect regression and did some statistical testing, and concluded that the last one is the best, the model that fits the best the data. And here I'm just showing you how this functional form in after being fitted, how it represents irradiant decay after hurricanes for different category and for a normalized distance of distance from the side to the eye of the hurricane divided over, this is the radius of the outermost closed isobar. It's just a metric of the size of the hurricane. So we formulated that, and this is the second part of the analysis. And then for the third part of the analysis, we used a numerical analysis done by Goodman in his PhD thesis, and he does numerical modeling of solar panel failure and assesses its or gives its probability, its fragility function here that you're seeing here. And you can see that in his fragility function, only category 2 hurricanes and above cause significant probability of failure in the solar panel. And you can see here what some examples of how they fail, with some failures on the railing or some failures also on the clippers. It's too high, like very high wind conditions can just make the solar panels blow or fly. We are I should say that we are reformulating this analysis because we got access to plenty of solar panel failures after Hurricane Maria. The Clinton Foundation and the Rocky Mountains Institute, they collected data on solar panel failure, both for rooftop solar panels and also ground mounted solar panels. So we're going to be also working on a next version of these solar panel fragility functions. So we put all of this together now, hurricane wind conditions, solar irradiance decay during hurricanes, and fragility functions also. And here we're modeling for different hurricanes, we're modeling time series of generation, doing a statistical simulation here. And you are seeing here wavy curves because solar, and this is after the time is in days after landfall, after the hurricane makes landfall. And you're seeing here wavy curves because irradiance goes down during the day, goes up during the day and goes down during the night, right? And this is for several hurricanes. And then on the plot on the right side of the slide, you are seeing the cumulative version of the plot at the middle. One is the instantaneous generation and the other one is the cumulative generation. And here I'm highlighting a few return periods for them. So for the worst hurricane, I calculated the return periods. I'm just highlighting them in different colors so you can see how bad it can be. And the first thing you notice here, and this is a specific plot for one site, this is in Miami, Florida. You can see that several of the storms are going to be spread around this dashed black line, and that represents just the summer generation. And that's because several storms are not gonna be affecting as much generation at day 4 because they don't have as high wind or because the cloud conditions are not as bad. However, when you move to the 10-year return period and upwards, you can start seeing worse performance. Especially when you go to a 1,000-year return period, that you can see also that there is no generation, and that's because the solar panel failed because of the high winds in the hurricane. So then we did the analysis. Also, we repeated the same analysis for other different sites, and this is Galveston in Texas, which is southern part of the U.S., Miami in Florida, which is on the east southern part of the U.S., also Hanover, which is a little bit more central, and New York, which is a bit more northern. And you can see some of the spatial differences there. The 1,000-year return period hurricane knocks down the solar panel in Galveston, Miami, and Hanover. In New York, things are a little bit better because the winds are not are a little bit lower. They don't have as much high risk of high winds as Florida, for example. But again, we are refining our fragility functions for solar panels, so this might change a bit. So now we focus on generation of. I'm gonna focus on generation at day 4, and so that's the y-axis at 4 here, and we're gonna see the reduction of this as a percentage of what it would be in the summer generation for the entire all the countries in the east coast of the U.S. And that's this plot here. So for the 10-year return period, you can see that the post-hurricane generation capacity as a percentage of what happens in the summer for the 10-year return period is around 70%. And in some places even goes to 50% at day 4, which is significant, right? 50% reduction is significant if in case of an emergency. And this is just a 10-year return period, so I was saying, and this is mostly driven by the hurricane cloud conditions that go along with a hurricane. Then when you move to the 100-year return period, you start seeing larger reduction in generation, up to 40%, and you can start seeing some very blue regions in Florida. And this is due to solar panel failure. Winds are already high that are causing some failures in the solar panels. And then when you move to the 1,000-year return period, you start seeing all the blue spaces, regions in several states in the southern east part of the United States, highlighting that these are at the highest risk of losing generation after hurricanes. If the grid moves to being solely solar, because here we're only doing the analysis on the solar infrastructure. Okay, so that was what I had for the hurricane hazard here. And just to conclude, I wanted to remind you that the power system is extremely vulnerable to natural hazards, as you can see in the previous examples for hurricanes, earthquakes, wildfires. And here what we're doing is we're developing some procedures, some frameworks to account for how these new technologies that are rapidly introduced to the power grid are changing the resiliency and risk of these communities. We're specifically talking about solar infrastructure and distributed energy generation here. We also saw the behavior of microgrid specifically for earthquake hazard. For the earthquake application in San Carlos, we saw that the adoption of 8.5% is still insufficient to provide access for people, access to energy for people after an earthquake aftermath. It's insufficient to sustain their demands. However, with a microgrid and adoptions of 20%, you're going to start seeing significant gains in resiliency, as you saw in the reductions of the risk metric, especially in the summer. And you can see that adoption according to net economic savings can lead to massive disparities here. So I think there's work left for policymakers to give incentives for neighborhoods that wouldn't be able to adopt if they don't have the incentives to adopt, so that they can have more equitable resiliency through their city. And the hurricane application in the East Coast points out to the fact that policymakers here and also structural engineers should be aware that there is of these higher risks that you have on the solar part, on the southern part of the United States, and potentially revise the code here, because now the solar generation, if it becomes the pillar of power systems, they need to be more resilient than what they've been designed for. They need to have a higher importance factor for design, and that's going to make a difference, especially for the places that you saw that are all in blue. So that's what I had with you. I just wanted to acknowledge my some of my funding sources and my collaborators here. And I just wanted to say that if you're interested in this work, I have some PhD positions available for the fall. So just contact me. And with that, I thank you. Thank you for your attention.
Thank you very much. Again, in a normal situation, it will be a room full of people clapping hands. Thanks a lot for your presentation. Very interesting. Specifically, I was amazed with the amount of hurricanes in Gulf of Mexico. That graph that you showed is amazing. And it was just for the last 20 years, this amount, like it literally every year, several of them happening. It's amazing. If anyone has any questions, please raise your hand and then unmute yourself. But if you don't mind, I'll start some questions. One thing, these microgrids, in a normal situation, are they connected to the main grids of the city as well? So they generate electricity in a normal situation, or they're just for the emergency?
On the normal situation, they are connected to the main grid, and they can give power to the main grid. So it's just they have this potential to work on island mode when needed. And
Okay,
again,
so
this is changing. Yeah.
Yes, please continue.
Yeah, no, I just was gonna say that the definition is quite blurry and the technology is changing a lot, but the main idea is that they share energy, they are connected to the main grid, and they can disconnect from it if the main grid has an outage.
This is perfect. So it's a win-win situation. So like everyone is encouraged to have these as well. So even the power companies are like encouraged to come and install these. So it would be perfect. Another thing is you have looked at a lot of energy consumption of households. Have you seen anything a little bit different than in a situation where the normal situation of consumption is and an emergency consumption? Have people's behaviors changed, or you don't have any data of that?
Yeah, I want to look at that. I don't have the data for that. The data we're using here was from, we got data only for a year of power consumption. I was in 2012, and in the US, I guess the event that happened in 20, but no big event happened in 2012. I wish I would have had data for like 2017 or 25 for different hurricanes or earthquakes. But no, that's something I really want to look into.
Yeah, it would be very interesting. I wish like Puerto Rico had some data after the incident that, okay, our consumption was this, now we have switched to this because it's emergency situation and like survival. Gemma, do you want to unmute yourself and ask your question?
Sure. Thanks, Luis. That was amazing as always. I think it's the first time ever that I've heard you not mention the word hospital.
Oh, that's true.
Congrats. So I was just wondering, so I have two questions in particular. Firstly, so I was just wondering, what is the kind of the time frame that you look at after the event? Like in terms of, do you look at like, you know, demand versus supply for a day or a month, or like how do you decide on the time frame that you look at?
Correct. Yeah, no, I think that's an interesting question. Now for the earthquake case, we only look at 1 day after the event, and I think we look also at 2, but that part we haven't published those results yet. We look at day 1, so all the results I show you here are at day 1, and that's because we wanted to focus on so all of these results are on day 1. We wanted to focus on emergency response, and especially when the grid is out. And usually the grid is out for a few days after the earthquake. However, if you want to look at hospitals, you would need to look a little bit beyond that, because hospitals or critical infrastructure in general have to operate over a longer time span, obviously, and that requires us to look at it over a different time span. But that also would require to merge this analysis with what would happen to the traditional power grid. Because here, all this analysis is a first cut analysis, but it's only on the solar infrastructure. It doesn't look at the main grid itself, at what happens in the distribution line. And that analysis, it's in the US, it's quite tricky. It's quite tricky because there's lack of data on where distribution lines are, for privacy, security issues, you name it. But that becomes one of the challenges. That's one of the reasons why we do it at 1 day. But I think we can still do some exploratory analysis into how this potentially could work with traditional power grid. It's hard to make this explicit analysis for the traditional power grid, but I think you can still do some more approximations on that end. But again, I think that's a quite relevant question, especially for the kind of stakeholder you're looking at. So here we're looking just at residential buildings for emergency response. If I want to look at hospitals, if I want to look at municipalities, fire stations, probably the 1 day is also important, but you need to look beyond that.
Okay, cool. And the second question is probably a bit stupid, but so you assume that the solar panel is non-functional if the building is red tagged, for an earthquake. Is there any way the solar panel could be, I mean, you obviously have to make an assumption, but is there any way the solar panel could be damaged without the building being damaged badly?
Yeah, for earthquakes, I don't think that's that likely, because its weight is very little compared to other non-structural components, and it's quite attached to the building, so it doesn't resonate as much. Maybe you might have some like wire failure potentially you could have between your solar installation to your inverter, where the solar panel is connected, or potentially to a battery. So that could happen. Where that's really important is for hurricanes. Wind can make them fail. And I mean, one thing I haven't done here, for example, in this analysis is so now we use some numerical simulations for here to map structural failure. But we saw from some pictures in Hurricane Maria that debris can also be important for damaging solar panels, and that's even tricky, right? Because debris can come from, it's not correlated with the damage within the building itself. It could, but it also could be correlated with the damage on other buildings. So that gets a little bit trickier there. But again, I think more work is needed here to see how these guys fell for hurricane winds. For earthquakes, I think they are more on the safer side. At least that's my take. Nobody has looked at this as much as they should yet, but that's just my intuition.
Yeah. Okay. Cool. Thanks.
Thanks.
Yeah, actually, that's very interesting. Because the battery of these solar panels are usually inside the building, if I'm not wrong. So an earthquake can damage the connection or the battery itself, while the solar panel might survive. I don't know a lot about solar panels. Can you tell me this, that are they in series or in the parallel? So if one panel fails, the whole system fails, or the capacity decreases, something like that?
Well, the panel itself is usually, they have a couple of ways to install it. They usually do one rails. They install rails to the roofs, kind of what you are seeing here. There are a couple of rails here, and they put other two rails on top, and they clip them with bolts, usually with bolts there. That's one way to do it. So usually they are quite, like the rails are quite independent from each other. In fact, when you have like ground mounted solar panels, you can see that a few fail and other ones might not fail, meaning that, failure can be localized in a few panels.
Okay, that's very good, specifically in hurricane, because if one goes, then the system can continue. Okay, that's good.
Correct. However, something tricky can happen also. And when you have like huge hurricane solar panel arrays, failure of one solar panel can make that damaged solar panel debris and a projectile that can make other panels fail also.
Oh,
that's when things become a little bit more complex.
So we should wish that it flies away instead of moving.
Correct. Or just design it much better, so that they don't fail.
Richard has asked a question in the chat, and is the energy storage system taken into consideration to increase the resilience?
Energy storage. So here for this analysis, we are assuming that they have enough energy storage. Energy storage is an issue. You need to have energy storage, because if not, if you don't consume your energy, the energy is just wasted. For solar, unfortunately, it's like that. Under normal conditions, you can sell your excess of energy to the main grid in the US, so you don't lose money, at least. But for these events where the main grid is going to be out, you need to have battery. And this is also tricky, because the way people do installations currently, when somebody buys a solar panel, usually they have the idea that, oh, I have a solar panel, I produce energy in my house, if the main grid is out, then I'm going to have power. But that's not often, that might not be the case. It depends. The solar panel goes to an inverter, and the inverter is usually on the main grid. And if the main grid is out, even if you have a solar panel, you might not have power. The way you have power is if your inverter is in your house, and that means that very likely you have a battery. So that's when you're like you're self-sufficient, or you don't depend on the main grid for generation. So battery plays a big role. But here we're just talking about battery sizes of, like the Tesla Powerwall that people are already installing in residential buildings. So I think in the future, this is going to become much more common to have your inverter in your house with your battery, than just having the inverter on the main grid. But yeah, again, battery is quite relevant for this, for resiliency, as it is also for the main work of on the regular hours of the power grid. Having said that, it's also, technology is changing a lot. It's quite fascinating to me. Me being a civil engineer, learning all of this, because it has been, obviously this goes beyond my discipline, my main discipline. Now we also have electric cars like the Nissan or the Tesla cars, and they are working also on vehicle to grid, but grid to vehicle also connection. So under an emergency, people are circulating the idea that you can, if your neighbor, you are one good neighbor, I would say, you can plug in your car, you can charge your battery there, and you can drive to another day, or your family. I know if you have a neighbor who's your family or friend, you can drive your car there and just plug your car back into their connection. So some people argue that that might damage the battery, but I mean, if you do it under an emergency, that should be fine. And the technology is already commercial. So I think the way in which we conceive sharing energy and after a disaster is gonna change a lot. You know, like in Peru, for example, I'm Peruvian. When there was an outage, and in the 90s we had a lot of outages, people just would, like, you know, throw a cord from like one street to another street, and that was also sharing energy, right? So the means are changing, but the concept it's quite similar, and new technologies are just going to enable that, I think, in many different ways.
Yes, very interesting. And yes, the future is the test of solar panels and stuff like that. Anyone else has any question? David, please.
Hi, Luis. Thanks for the presentation. It was really interesting. I had two quick questions, if it's okay. One was, in the earthquake case, do you know how dust affects the solar panels, if it does at all? And then for the winds, do you know how high your solar panels are installed, or do you take that into consideration at all? Thanks.
Mm-hmm. Oh, when you mean just dust that can cover the panel?
Yeah. Does dust get released when there's an earthquake? Maybe.
I am not aware of that being an issue. No, I haven't looked at that, but I haven't heard that that's also. I haven't read that that's an issue. So we didn't consider that in the analysis. Yeah, and then for your second question, well, there are two main ways to install panels. For residential, commercial, usually people put them on top of the roofs, like here. They are usually very, like, just on top of the roof, not much height difference between the roof and where the solar panel are. So that's one case. The other case is ground mounted, and they are just on the ground, and they put the rails on the ground again with some foundations there, and that's a little bit higher. So now there are this PhD thesis, Goodman here, he argues that out of wind tunnel testing, the pressure coefficients are quite similar for both, but that's the only data point we have to kind of answer your question in terms of the height. They seem to be, wind seem to be inducing kind of the same pressure for both cases, but there is no, I wish there would be more testing, like a wind tunnel testing for them to see what are these pressure coefficients on them and reformulate them in the code. But yeah, that's the only thing I've seen kind of with regards to your question.
Oh, that's great. Thanks.
Anyone else has any question? One quick question. I think this will be the last question. I won't bother you more. Regarding that microgrids, how big can the grids be in terms of like kilometer, or in terms of like how many households it can cover? If you know, like.
Yeah. So for example, here what we modeled was sizes from 20 houses. Where is it? From 10 houses all the way to 50, 60. And
this is San Carlos one.
In San Carlos, yes. And from an electrical viewpoint, that's totally feasible. It becomes a cost problem. What's the most effective cost for the microgrid? When we're talking with the electrical engineers in our team, we're confident that the technology to build the microgrid is not an issue. It can be designed in many ways, but it becomes more of a cost problem, and that's changing a lot. It's hard to have a number for the microgrid because it depends on the specific technology itself, and it's not clear how they're going to be in the future. Having said that, like New York, for example, New Year's are investing in like new companies that for them to build roadmaps to building microgrids. Princeton also has a microgrid, and they vary in sizes. I don't have the installed capacity numbers on top of my head, but just my take on this is that the technology is there. If you want to build like a microgrid for 100 houses, or 5 houses. Both are totally doable. It becomes a cost problem.
Yeah, makes sense. And definitely San Carlos, the way the buildings are compared to, for example, New York, that in one tower there are 200 residentials.
Correct.
It can be an issue or not, I don't know. Again, thank you very much. It was very interesting. If you don't mind, I'll just share my screen for a second.
Sure. Let me just stop my...
And yes, so we will continue our EPICentre seminars until Christmas, and then we'll have new ones after Christmas. So next week, as you all know, will be by Dr. Roberto Gentile, the hysteretic energy-based state-dependent fragility for ground motion sequences. We'll continue the weeks after with Victor Mellati on dissipating systems for seismic protection of historic masonry structures. And before Christmas, we will have Dr. Marco Bogueira talking about advances and challenges in tsunami assessment of buildings and critical infrastructure. As always, please consider that everyone who is in UCL has free access to LinkedIn Learning, full of resources. Make sure that you use them. Our social media, follow us so you have all the information. Again, please join me in thanking Luis. Very interesting presentation, very useful and very important for the future. I don't know how to use the reactions, but I'm clapping my hands.
Thank you very much, everybody.
Thank you very much. Thank you for joining us as well, and we'll see you next week. Thank you. Bye.
Thanks, everyone.